Okay, covalent bonds. So we talked about ionic bonds, now we're on to covalent bonds, and the best way to describe this is with this potential energy diagram. This is zero energy, so this is on, we call it potential energy, the energy that's stored in the bond. Now, way far away here we have two hydrogen atoms that are separated from each other, so the potential energy between them, the attraction between them, is very slight. As they get closer together, though, they start to fall into this potential well. If you recall, either in my lecture or in the book or earlier video lecture, when we talk about negative energy, we're talking about energy of binding. So when it's zero, that means that these hydrogen atoms don't notice each other at all. But when it goes negative like this, now this is showing the energy of these guys being very close, so they're negative, means that they're attracting each other. And then when they're overlapping each other, and there's a bond, that's when we're at the lowest point in this potential energy well, and this would be considered, so this is distance, so we call this the bond length. So this is, here, this is zero. This is where they'd be completely overlapped, which isn't allowed. And then this is the bond length. And then also from here up, this is the, let me just write it on the side here, bond dissociation energy that we'll see at the end of the chapter. So if you want to break this bond, you'd have to put in the energy from here up. You'd figure out how much energy that is, add that in, and the bond will break. So that's how the covalent bonds are, the overlapping of orbitals, and they're very strong. So use Lewis symbols to describe covalent bonding. Do a very simple covalent compound, HCl. Hydrogen is in group 1A, so it has 1 electron. Chloride is, but it's not ionic, it's not a metal, so it doesn't act like a metal, it doesn't form an ionic bond. Now the difference here, remember a previous lecture I had lithium over here. Lithium doesn't give, lithium gives up its electron. The hydrogen doesn't. It just shares it. It gives it to the chlorine, but it follows along. It doesn't just throw it over to the chlorine, and the chlorine gives up its electron to the hydrogen, and they end up with 2 electrons between them, and now you have a covalent bond. So this represents a covalent bond, a sharing of atoms. And we can also draw it as one line. Okay, use Lewis symbols to describe coordinate covalent bonding. And now, if we have, normally we have A plus B come together, and they both bring an electron to the party. They both bring an electron to the bond. But if A came in, and A and B just represent some general species or general atom. So we can have, even though this one doesn't have a dot next to it like this one does, that's okay. It's not ionized form of A. A is just whatever we want it to be at the moment. So B is not boron, it's just some general form. Now, some general element. So this element has 2 electrons. This one has 1. Notice they still form the same look of a bond, but coordinate covalent bonding means that one of the atoms or one of the species brought in both electrons to the party. That's the thing. They form the same bond, and once they formed, you can't tell them apart. But when they're forming, when one of the elements brings in the 2 electrons to the same to the bond, and the other one brings none, then that's called coordinate covalent bonding. The octet rule is what we're going to use to guide us in a lot of the structures we're going to draw. And this is the tendency of atoms and molecules to have 8 electrons in their valence shells. That's what we're always shooting for. So fluorine has, actually, go back up to here. We have chlorine has 7 electrons. By adding the other hydrogen here, we get 8 around the chlorine. Now hydrogen is an exception to the octet rule. It's too small to get 8 around it, so it accepts 2. So let's look at something like fluorine and bromine. They're both halogens, and they have 7 electrons, and if they share, then they each get, now there's only 14 electrons, so they can't each have 8 because that'd be 16 electrons total. But if they share them, they don't know the difference. This bromine says, I got 8 around me, and fluorine says, no, I have 8 around me. So they don't mind that they're sharing with the other atom as long as they have those 8 around them overall over the course of time. So, and then something more involved like nitrogen and fluorine. Now, nitrogen, to complete its octet, it's not enough for it to share with fluorine once. It has to do it 3 times. Each of the fluorines only needs to bond once to complete its octet. But the nitrogen needs to bond 3 times. So since each fluorine can bond once, we need 3 fluorines, and we end up with, and we'll find a way of not having to draw all these dots out. If you in your last class don't know how far you got as far as the structures, but for now we're going to use all the dots, and you can see that we probably don't want to do that each time. But you can see that each of the fluorines has its 8, and the nitrogen has its 8. So it's completed as octet, and generally when that happens, it means it's a stable molecule. Now there's many exceptions to that, but to start out, it's a really great way to look at bonding. Okay, then Lewis symbols to show single, double, and triple bonding. So we've done this already, but let's where we had say fluorine and bromine. Now there's a single bond. This is 2 electrons. A double bond would be like oxygen. Oxygen, I'm not going to take a lot of time to explain how we got this. We're going to be doing a lot of these later. But when there's 4 electrons between 2 atoms, then it's a double bond. So that's 4, or 2 pairs of 2. And then if we have nitrogen, nitrogen has 3 pairs of electrons around it, or 6 electrons, so this is a triple bond. So just so that you know that that's possible, we're not going to explain how we got there at this point. And then you can reduce this down to, say, fluorine, just show a single dash for the 2 electrons. This means the same thing. I'm going to do this real quick. Oxygen, you can see that looks a lot better. And this one especially, when I look at it, I kind of, what's going on here? Nice, triple bond. You can see that right there. So just to let you know that these exist and what they look like to start with, and we'll be dealing with them a lot more later.